addition to summarizing the...
It's Marta Verweij, and she'll talk about, and give us the first introductory talk, an experimental overview of groomed jet splittings. So go ahead.
This is the point.
Yes, that.
Yeah, so thanks for inviting me, and it's really nice to see all of you indeed after such a long time. So I look forward to the discussions. So the organizers asked me to give an experimental overview on groomed jet splittings. Now, grooming is a tool, not so much physics. So I will try to put some physics in there as well. But I will really focus on the groomed measurement. So it's not a complete overview of all jet substructure, but we will have plenty of time to discuss the other measurements as well in other talks. But of course, you do grooming when you do jet substructure and to study the dynamics of particles inside the jets, where there are basically two important scales, the angular and the momentum scale, although you can express them in different variables. We start seeing a lot of KT. When we look at jet substructure, then we can look at all the hadrons in the jets, yeah, so the fragmentation functions, which we have been studying also a lot in heavy ions, or the classic jet shapes like the angularities, which I will actually show today. And then the groomed observables, where there is some algorithm which removes some part of the jet, which you find less interesting or to really focus on a specific aspect. So I think you are all very familiar with this. And what we try to study is to see if the quenched jet substructure is different from the unquenched jet, and why would we do that? We want to see how the full parton shower is modified in the medium. So we know jets lose energy, but how do they lose it exactly? And for that, you need to study the full parton shower, because a jet is not just energy loss of one particle. Well, it could be if it's fully coherent. But in order to see if that's the case, we have to look at jet substructure. So what's the exact mechanism for modifying the parton shower? And then in the end, the last step is to really connect that to medium properties, which we try to do right now with model comparisons. But we still have many steps to make, so I hope we can have some fruitful discussions about that. Okay, so why grooming? Yeah, so okay, we lose energy, the jet loses energy. One thing we are really after is how this medium-induced gluon spectrum really looks like. Of course, we have theoretical calculations, so we would like to understand which one is correct and what are the important aspects. And at least my personal hope was that by doing grooming, we would really able to isolate the individual radiated gluons, which is necessary because if you don't start to isolate it, really you get competing effects. So there's one example on this slide, which is the ungroomed jet mass, which when we measured this, we were somewhat underwhelmed because the data was exactly compatible with the vacuum prediction. But then when you start comparing to these dual curves, you see that there are two competing effects, the medium-induced gluon radiation and the recoil, which somehow miraculously cancel. This is not satisfying. And of course, it's a clear sign that you have to try to disentangle the different effects. Either focusing on one or the other. You can go both directions, both have advantages, of course.
Hi, nice to meet you.
Hello.
How are you?
Good, how are you?
So we can hear you.
So you can use this table. Here is a key. You can enter. I'm not here.
Okay, I will just continue. Okay, so by now we know that it's not just about jet energy loss, but there are many more things going on in the parton shower. Yeah, so we have the medium-induced energy loss, which can be either in cone or out of cone. We have coherence effects, so it will be very good to see what this critical angle is, since that really depends on the properties of the medium. And then, of course, the recoil, which pops up everywhere in our measurements, it seems. Okay, so why grooming? Well, we have some preference to really have theoretically well-controlled observables, and grooming is one of the ways in which we think we can achieve that, so that we can compare to PQCD calculations. In addition, it allows you to have a bit smaller experimental corrections because you become less sensitive to to the soft hadron production, which generally is harder to correct and difficult to control. Although grooming also has real disadvantages, which I will talk about. But we mostly use it to really focus on some specific areas and really zoom in into specific areas of the radiation phase space. Okay, so if you look at the hard splitting and use it as a probe of the medium, so grooming allows you to specifically focus on the hard splittings. The idea there is that you let this parton split and then you look at the antenna propagating through the medium and look at the influence it has. And with different tools, you can look at the angle, you can look at the momentum sharing, or a combination of the two. So a quick recap about grooming. So you have to order your constituents in the way you like. So for most measurements currently, we use the angular ordering, and then we start this declustering process where we walk through the history until we find a splitting that satisfies our criteria. And then you study that particular split, but you don't have to limit yourselves to this first split that satisfies the criteria. In principle, you can use all splits in this tree, which should resemble the parton shower, to study also later splits in the shower. But most measurements actually focus on the first split. You have to define your observables. So two of the observables you've seen a lot is this momentum sharing ZG, which is the momentum fraction the radiated branch carries, and also the angle between these two branches at the first split in which your grooming conditions are met. So this was the first measurement, which we did in CMS, where we looked at this momentum sharing as function of jet PT. You can see quite large experimental uncertainties, but the overall picture you see is that for lead, the splittings are a bit less balanced. Yeah, so you see a bit of enhancement at small ZG and depletion at large ZG. You can see that the models capture this actually. There is some variation within the models, but it stays well within these experimental uncertainties. But these models have different physics mechanisms in there. So in case of Jewel, it seems to be mostly caused by the medium response, which promotes a subject which otherwise wouldn't have passed the grooming condition. Well, for the coherent antenna picture of BDMPS, it's really the coherent energy loss. And the same for the higher twist calculation here. It doesn't really allow to distinguish between this, since all models capture this trend. Now, there's another thing about this measurement. So this is not unfolded. So instead of fully correcting it, the experimental resolution was folded into the PP reference in order to make this ratio and do the comparison. And in recent years, we have seen a lot of improvement on that. On top of that, for this measurement, the distributions were self-normalized, so you were losing the information about jets that would never satisfy the grooming condition. This was all realized and improved now. A similar study was done in the low PT regime by Alice, where you see actually a quite similar picture of indeed a bit less balancing in lead collisions. And on the left-hand side, you can see a calculation by Paul and collaborators, where you can see that, okay, with this independent energy loss of the two branches, to affect, so the red line is the incoherent energy loss, and it's all competing again. So, you have to somehow balance this, but we are clearly more consistent with the blue line. And in addition, okay, that's not in this model, the promotion of the subjects due to medium response, but it all comes into this observable. Okay, then the other measurement, which actually Yi worked on a lot, is the groomed jet mass. And in this case, there were different areas of phase space were investigated. So there was a flat grooming where you have this red line and where you groom away everything which is below some momentum sharing threshold, but also this blue line where you groom a lot more and you really focus on the core of the jet. Yeah, so you see that you groom away all large angle radiation, basically. It's very large R, you groom everything, But for small R, you actually allow soft splits to come in. So on the right-hand side, you can see that let over PP ratio for this groomed jet mass, and you can see that for this large angle grooming, so where we focus really on the jet core, there is almost no modification. So the jet core is hardly affected. Looks the same as in PP collisions. And for the flat grooming, you actually see a small enhancement for the very large groomed jet masses. And you can see that, Dual has doesn't necessarily catch this exactly the way it appears in the data. Actually, the two versions of Dual with recoil on and off go either too high or too low. And somehow the broadening effect, which is in Cupicia, agrees with this measurement, but we know that there are many other measurements where Cupicia has a too big broadening effect, which is groomed away here. That's why you don't see it here. And then the PT dependence was also studied. So on the right-hand side, you see the flat grooming case where you see this small enhancement at large groomed jet masses. So you see that this slowly goes away when you increase the jet PT. So somehow when you increase the jet PT, you naturally start grooming, well, in absolute scale harder, and somehow it goes away. So it seems to be at a fixed PT, the effect which is in there. Okay, so yeah, there are quite some limitations of grooming in heavy ion collisions. Yeah, if you do these grooming selection cuts, you're really selecting an area of radiation phase space that you're interested in, but you're also cutting into the resolution you have in heavy ion collisions due to the large fluctuating background. You also have this effect, of course, in PP collisions, but it's enhanced in heavy ion collisions. And truncations for an experimentalist are really hard to deal with because it's not a simple smearing. It has a cutoff, and then you get unexpected effects. And I just show you an example here, illustration, these type of effects from Alice, where they show the response matrices on the left-hand side for the ZG and the right-hand side for the RG. You can see in both cases large off-diagonal structures. In this case, this is because splittings which in vacuum without this large underlying event wouldn't pass your grooming criteria in the large density environment actually pass it because they get promoted, and this is the resolution effect. But it's bad because you look at a different splitting than what you intended to look at. You're actually looking at the fluctuations of the background. And this is exactly why these first measurements were compared to folded PP, because there you can build it in, but to undo this is, impossible. But of course, James and company have studied a lot. I think this is a plot of yours, where you can actually do more selective grooming to reduce this effect. So on the right-hand side, you can see different grooming settings, and you can see if you increase this Z-cut, so the minimum momentum sharing that you require for the splits of interest, then this effect goes away. Of course, the Z-cut you need depends on how large your background is, but you can get rid of all your misidentified splittings. It comes with the price of also cutting some possibly interesting physics away. Some of these radiated gluons might also have rather low Z, and you remove them as well. But if your background is much larger than your signal, it's worth doing this. Another way is to simply go to less central events. If you make the background smaller, all these effects get smaller. Of course, there the disadvantage is that you have a less hot medium, so also your jet quenching effects get smaller. So it's always a trade-off. And then there was a lot of effort put into actually improving our background subtraction techniques. So as you probably know, we always take the whole event as first start subtracting background before we do any analysis. And there were some improvements done. So these plots are specifically about different versions of the constituent subtraction. So we started off measurements with these jet by jets. So the red line where you see this giant second peak in these RG distributions, these are all misidentified splittings. But if you use the more modern version, so the event by event, where you actually consider the entire event instead of just one jet, this effect already gets smaller, and in this way you can improve your measurements and actually make unfolding possible, which makes a comparison to theory possible, which then, okay, we can learn, it's a multi-step process. So this was all done, and I think it's great work. So here you see a fully unfolded result now with a z-cut of 0.2 from Alice in central atlet collisions. And in the bottom, you see, well, the ratio between atlet and PP. And okay, within these experimental uncertainties, you don't see any modification. Yeah, so there's none. And you can also see for the models, there's not much. Yeah, most of the models also have an uncertainty, and within that uncertainty, there's also no modification. So either this whole splitting function is not modified at all, or it's happening at lower z scales. So yeah, it's interesting to see now. In addition, the splitting angle was also measured. So the angle between these two branches, so theta g here, you can see, okay, in red, the lat, in blue, the PP. You can see that distribution in lat is a bit shifted to the left, so to smaller angles. If you take the ratio, you see an enhancement at small angles, which might mean that, okay, you have less of these vacuum-like emitters there, from which you can radiate the energy, and then you observe less suppression in the data. At the same time, you observe a suppression here at large theta g. So maybe there we are dealing with very wide jets, which have many more partons inside the parton shower, meaning you have more partons who can interact with the medium. So higher probability to lose more energy. So there you see a higher suppression. Now, this is, of course, just a interpretation of this data. Might also very well be a jet selection effect, because these are inclusive measurements. So the PTs of the jets are restricted here from 60 to 80 GeV, and this means that the overall ensemble of jets we are looking at in lat and in PP collisions is different. So you have feed in from higher PT, and this RG behaves exactly like this. I will show you some plots, and there might be a flavor difference. So we have to be careful with these interpretations.
This P selection is similar to for the last plot when you plot the minimum fraction, is it?
Yes, the selection is the same. So it's again this z-cut 0.2, but you see now that, yeah, exactly. So yeah, also 60 to 80. Oh, so yeah, so Xinyan asked if the ensemble of jets basically is the same between this ZG and this theta G measurement of Alice, and yes, it is exactly the same. But you can see that for the ZG, apparently this enhancement and suppression we see in the theta G is somehow spread anywhere in ZG. You don't see it directly coming back, which is of course possible. And we don't have the 2D correlation, so, but yeah, there's a bit of interpretation. Yeah. So now I wanted to quickly flash this theory calculation by Paul and collaborators, where they show what happens in this coherent decoherent energy picture, where there's this critical angle, and you see that okay, if jets have a split which is larger than this critical angle, then you get suppression. Well, if the split is smaller than this critical angle, well, you get an enhancement. So this type of trend is what we see in the data. So the question you can ask yourself is if Alice is seeing here the critical angle or not. Maybe it's due to the number of emitters, or maybe it's a selection bias. Yeah, maybe we see a narrowing due to the jets which we select. And here another model calculation from the hybrid model, where again you see also that they predict that for small angle here you see an enhancement, and for large angle in red you see a depletion. So it seems it comes out of many models. If you look at less central events, you get actually a very similar picture. So on the left-hand side, again, with the same selection on the momentum fraction of the radiated branches. And you see that also 30 to 50% centrality, although the modification is expected to be smaller, it's still visible, and the experimental uncertainties are somewhat smaller, or at least the systematic ones, statistically not, because we get less jets in those centralities. On the right-hand side, you can see a study which I also find interesting, because here a z-cut of 0.4 was used. So that means that very balanced splittings were selected. And also for these symmetric splittings, you actually see quite a similar modification, which is not completely seen by the models, but then okay, the models also find it hard to go to these very small angles. So it's a bit incomplete picture in that sense. But okay, at the large G, you can definitely see that this hybrid model version with this resolution length set to infinity is disagreeing with the data, which you can also see on the left-hand side. Okay, so now we have also seen an atlas measurement of exactly the same observable, which okay they call RG, but doesn't matter. It's the same thing with the same z-cut actually of 0.2. So we can compare quite directly. On the left-hand side, you see the suppression. So they haven't normalized by the total number of jets in the sample, but really they measured the cross section, which allows to plot the RAA. And you see it for different selections of RG. Yeah. So we have an inclusive one which you can compare to that. This is the black one. And then you can see you go from large angle to small angle, which okay maybe is easier to see on the right hand side where you see it plotted as function of RG. So you see that the suppression the jets are less suppressed if the splitting angle is small, while if the splitting angle is large, you see much more suppression, indicating that maybe the white jets indeed lose much more energy because there are more emitters in there. Again, here also the effect of the jet selection needs to be studied because these are competing effects. The reason I want to show you here, so these are these RG distributions as measured by Atlas in PP collisions. Left-hand side, low PT, right-hand side, high PT. And you can see if you go to high PT, this distribution shifts to the left. So if you have energy loss and you get feed in from higher Q-square processes, this is exactly the effect you expect to see. This might not fully explain what the data shows, as we have seen for the fragmentation functions. But my question to you is, so how much room is there really for this decoherent energy loss picture? Both for the Alice and Atlas measurements, of course. Then I discovered something I found quite interesting. So Atlas actually also varied the beta parameter. So this is this influences what you groom on the angular scale. On the right hand side, you can see okay again a bit of such a grooming picture. So you groom away everything which is below these lines. The z cut 0.2 and beta equals 0 is the red line. That is what we have been looking at. So no angular dependence on the grooming. Then they did a variation where they set beta a bit smaller than 0, minus 0.1. That's the blue line. You can see that then you'll get very similar results because okay, you just groom a bit more at the small angles. There has no big effect. You get similar suppressions. However, they also tested beta equals 1, and that really opens up a lot of phase space. Oh God, okay, I will hurry. So as you can see on the right-hand side, then you keep everything which is above the green line. So you start accepting a lot of soft variation. So, well, you will find much earlier a split that satisfies your requirement, and you're gonna find them at large angle. Now, if you specifically focus on what happens with the suppression of jets with a very small angle, so smaller than 0.2, yeah, then you see actually that this beta equals 1, you find jets that are much less suppressed. So you seem to be recovering something here. Okay, and this actually what you see here, just wanted to point out that that's very consistent with this earlier measurement where big jets were made out of small jets because, well, starting from the second data point, you're actually looking also at angles above 0.2 or so. And so this suppression value is consistent with this large RG suppression value. So it's good to see experimental consistency with these different methods. Okay, a bit about angularities. Yeah, so okay, these are the generalized angularities where you calculate the jet shape summing over all the constituents, and you combine well, the z and the angular scale, and you vary alpha, which allows you to put a larger or smaller weight on collinear radiation. So you can see here the Alice measurement on the left-hand side for ungroomed, right-hand side for groomed measurements for different values of alpha. So alpha equals 1, the black points, that's the jet width. Alpha equals 2 is proportional to the jet mass, to give you a bit of an idea. You can see actually in the lower plots, if you look at the ratios, that for the ungroomed case, any modification is not very significant. But you see for the groomed case, their experimental uncertainties are smaller, and you see a modification. Where also here, okay, we are dealing with competing effects. The suppression of white jets and broadening effects. But with the jet grooming, we are of course focusing more on the collimation effect. So we are narrowing in on the narrowing of the jet. Okay, I just continue. Your comparison to models, where you see that most models actually describe these modifications we see in the angularities for the data, except dual. But actually, this is a baseline issue, as I will just show you. So if you see models deviating in such a ratio, that doesn't always mean that the physics is wrong. And you can also see here the comparison for the models for these different weights on the collinear radiation. You can see the effect in data where this somehow this turn on is sharper for larger alpha. So when we focus more on the collinear radiation that's reproduced by all these models. Okay, then a word about the baseline. So here we compare directly these angularity distributions to the models on the left-hand side. You see for PP collisions, and we just saw that dual doesn't reproduce the lead over PP ratio, but this seems to come from the PP baseline, which is very different from the data. So okay, this I think is a Pythia tuning issue, which probably can be fixed in the future. On the right-hand side, you can see quite some variation in the models if you do this comparison directly in the data, but currently our data doesn't have enough distinguishing power, so it overlaps with the uncertainties. But there's quite a spread, so with more data, this should become better. Okay, this is not visible at all, but what we are going to look now at is another jet substructure observable, which probes the angular structure by using the jet axis. So you have a standard jet axis, which you just get by adding up the 4 vectors of all the constituents in your jet. You get a new jet axis when you do grooming, when you remove parts of the jet. But you can also take this winner takes all approach, where in each recombination step, you let the new vector you're forming in this recombination step pointing into the direction of the highest PT branch of the two that you're merging together. So this doesn't mean that the jet axis points in the direction of the highest PT particle in the jet. It can mean that, but not by definition. Yeah, so it is really a recombination plan. The reason to do this is because if you study these angular structures, you can hopefully distinguish between effects like medium-induced radiation and PT broadening, which give opposite effects. Okay, so here you see the measurement, where the measurement now is looking at the distance or the angle between these two, between these different jet axes. So in the black line, you see this WTA axis minus the standard axis, and then the two colored data points, red and blue, is for 2 different grooming scenarios. You can see that actually grooming doesn't change the picture at all. So the groomed axis is very close to the standard axis. Well, actually WTA axis is pointing quite in a different direction. We like the WTA axis because it's much less sensitive to any background fluctuations, to any recoiling effects. And we see here, as for other observables, again, this narrowing effect for this jet selection. Yes, I'll make it. You can also compare this to the model. So now we are not looking at the groomed result, but just at the WTA minus the standard axis. And you can see that almost all models reproduce this. Well, like we have seen for theta G, I think this is similar, except one. So you have this PT broadening model. And there there's a disagreement, which we also saw for theta G, but okay, interesting on this observable in general, there's no grooming at all. Yeah. So the fact that this PT broadening model doesn't agree with our theta G measurement is not due to grooming. The effect is really too big and not seen in the data. And also for all the other model comparisons here, you have really an ungroomed measurement of the jet substructure. Which is, okay, theoretically well-controlled observable. Okay, then I want to say a few words about dynamical grooming, which works a bit different from this soft drop grooming, because, okay, the The idea is here that you find the hardest split in a tree, the whole branching tree of your jet. And this whole cutoff, well, depends on the jet properties, and you can adjust the type of hardness that you're looking for by this parameter A here. So that is what is done on the right-hand side, where you see this parameter A varying. And this is in PP collisions, but you see the comparison to Pythia, and okay, the data in Pythia seem to agree. So that this is apparently something we understand. And you see also the soft drop with the Z-cut 0.2 as a comparison there. Okay, here we focus on heavy ions. So here I show you the heavy ion result. So you see the PP in purple and the heavy ion result in orange. You can see that in the region where we can actually measure this in heavy ion collisions, the PP and let is consistent with each other. So we don't see a Parton shower modification here. And we cannot distinguish between the hybrid model, well, the normal hybrid model, and the hybrid model with this Molière implementation, this implementation of hard scatterings. Although, okay, I think there is some future perspective to actually do this with a measurement of the groomed KT. Here, a measurement of the groomed KT, but now with the usual soft drop, where we can span a larger range. Here you can see again a sort of narrowing effect. So you see an enhancement at small KTs and depletion at high KTs. So this is consistent with the other jet substructure measurements. And then here finally a comparison between all these different dynamical grooming methods. You can see that okay, at high KT they all give quite a similar measurement. And this is really due to experimental precision currently. Okay, then I want to flash these results, which have nothing to do with grooming. But these are the Z hadron measurements of Atlas and CMS, and I really find them very interesting because I have been pointing a few times into the effect of the jet selection and really using the Z as a tag, or if necessary, the photon would really help, and then to really do jet substructure on the away side to get these theoretically well-controlled observables with as low jet PT cut as possible, because otherwise you get these jet selection effects. Again, I think this really goes in a great direction, and of course with this Z plus hadron you can spend such a large area of phase space. But okay, we have talks focusing much more on this measurement later on, but I'm really looking into the power of these type of measurements in the future. Then okay, jets are really never simple. Yes, it's a zero, so that's good. And it gets really much more complicated when you are in the quark-gluon plasma, because we have so many mechanisms affecting our Parton shower that we have to deal with it. But I think grooming is a great tool to zoom into specific areas, but it also has some clear disadvantages. So it would be good to look forward and look at new possibilities because the cutoff effects are severe. And it would be good to retrieve also the smaller Z scales if possible. Okay, so our chair is standing, so I'm going to finish.
So thanks so much, Marta, for this very nice and thorough overview and introduction to the workshop. So let's open the floor for questions. I think Yenji can start.
Thanks a lot for the very nice overview talk, and also congratulations to all those very nice measurement with inclusive jet. So all those measurement points to narrowing effect, and also can be reproduced largely by almost all the models. So does that mean basically what we have learned from the inclusive jet is just a narrowing?
Yeah.
And is there any plan to look into, for example, the recoil jet in the digest system or photon type jet, which can overcome the survival effect partially? Yeah,
I think this is an important thing, because the fact that you see narrowing doesn't mean that the effect of jet quenching is narrowing. It might be very well broadening. So yes, indeed, photon jet might be something we can look forward to. But I would also, for Alice, I would also not exclude hadron jets. Yes, so this gives the complication that the hadron comes from a quench jet as well. So there is some energy loss effect there as well. We have seen that in our most recent hadron jet measurements, that there's an interplay of this energy loss. But of course, it allows you to have a very large statistic sample, which has these advantages. And even changing the PT of the hadron allows you to actually play with this interplay between the different hadrons, with different energy loss you have. Yeah, so yes, this is definitely something to look at. Yeah, Xingyan.
Again, thank you for the very nice overview. So I have like one comment, right?
Your mic stopped.
Yeah, so I don't have to press all the time. Well, the comment is about the role of recoil versus radiation.
Yeah.
And if you look at in detail in the transport model and even the recoil, for small angle scattering, their spectrum almost indistinguishable from the soft radiation sometimes.
Oh, yeah.
So all this grooming is not necessary just only on effect of the soft radiation, but it can also with the same thing effect on this collinear scattering too.
Yeah.
So this is just a comment. The question is regarding you have two plots. Like one is that the momentum fraction, which has in the beginning of our talk, you don't see any separate modification. On other and the angular, you see sort of like modification. So does this mean that can you actually look at in certain region of angle how that momentum fraction will also be modified?
Yeah, I think it means what you're asking for is to have a correlation measurement between ZG and theta G, and it's definitely on our agenda. Yes. Yeah. Yes, you have to be able to understand exactly this interplay. Yes.
Hi, Marta. Thanks. A very nice talk. I certainly very much appreciate your comments about the need to span a broad phase space. Grooming has its limitations, as we see. I mean, it's very powerful, but relatively small R and large PT, and kind of moving us out of that phase space perhaps requires different approaches. And you alluded, or not explicitly, but I think you showed one such substructure observable, the angularities, which aren't needed where grooming is not required, but there's actually a broader class of such observables: end-subjettiness, energy correlators. And you can take this either as a kind of question, comment now and comment on it, or we can kind of defer it to the discussion later. But I think a kind of broad discussion about the physics behind those and what one might expect, for instance, from energy correlators in medium, what are the predictions? And from my point of view, from experimentalist, these are amenable. No surprise, I should comment on this, on the statistical approach to background mitigation, which I think could then broaden the phase space rather considerably. So maybe this is a comment or take it as a question. For me, this is an important path forward to explore.
Yeah, I mean, I fully agree. I mean, we see with the grooming, we are restricting ourselves to rather large momentum cutoffs. And the method you mentioned would allow us to possibly actually re-enter the small energy phase space, which where there should be a lot of physics to be learned. Of course, this talk was focused on groomed jet observables. That was the task. So
let me just note that, in fact, using not these techniques, but looking at our recoil, we're actually seeing at very low PT. We're now seeing quite striking effects, which may be kind of related to what happens to energetic jets and how one recovers what gets lost. So I think these kinds of correlations we perhaps are now seeing in the data, and one should try to go after them with substructure as well.
Yeah.
Okay, we still have some time for questions. There's one online. So please go ahead online. The one who.
Hi, Marta. This is a very nice overview talk. My question on your slide 2021. Yeah, particularly that's same GG and RG discussion.
Yeah.
So the point here is that whether G cut, which is here is 0.2, is important, or we need to explore the lower jets PT range. That is important. So because when we look at GG, there is no difference, but when you look at theta G, there is enhancement. So the question is whether GG is important or the lowering the kinematic range is important.
Yeah, so your proposal is to go to lower jet PTs?
Yes.
Yeah. So now, so the experimental problem we have there is that our background is an absolute scale, so it doesn't go down. So if we go to lower jet PTs, the Z-cut becomes less efficient and you will get back this off-diagonal problems. So I don't think these specific observables are very suited for that, and we really have to go to these energy correlators, different types of measurements. And you can actually see, okay, in some sense, the Z hadron type of measurements, they allow to go into, and photon hadron measurements, they allow to go into this regime. But then we have less theoretical control.
Okay, and you showed one of theory calculation, probably 21 or 22.
This one?
Yeah, this one, yeah, the right side plot. So do we have such, such type of calculation for ZG? What do we observe?
Yes, but I don't think I have it. So yes, and I think it's even in the plot. So the blue line, which is labeled Cocal on slide 18, is from this model. So it actually shows a bit of slope in this blue line. So you can see a bit of depletion at high Z. But okay, we don't see this in the data, but it is also consistent with the data because, well, these uncertainties are large. That we can get smaller experimentally, of course, with more data.
Yeah. Okay.
Okay, thank you very much. So I think we have to move on. If you have more questions, don't forget the discussion session at the end of the day today. Thank you, Marta, very much.
Thank you.